All right, I think it's working. So yeah, computer science and other disciplines, because we've been talking about, right, computer science, just as far as computer science is concerned. Like, this is what software engineers do all day long, but computer science exists everywhere, right? Everybody has a computer in front of them at work most of the places that you could work these days. So that is kind of influencing what we should talk about, right? So let's talk about CSCI in other places, because it's not true, right, that everybody is just walking around, open up Python and making turtle programs every day. I'm teaching you that because it generalizes to whatever you might go and do with programming, okay, with computer science. So yeah, let's talk about what other people are doing. All right, let's talk about social science and art, some places that maybe it's not immediately obvious that people are doing computer sciencey stuff. They're doing software engineering. They're making stuff to apply to these fields. So we need to talk about that. So I think I want to start us off with a question. So please get into peer instruction groups, say hi, talk about what you did over the break, and please go to the written ice page because I have something that I want you to write down. I'll clear it out as usual. Thinking about those specific fields, the fields of social science and the field of art, what are people doing? What are some examples of people using software or writing software to advance the fields of social science, to advance the fields of art? Any questions about the question? Just see if you can rattle off anything off the top of your head, and I have some examples for us after that. Okay? So take a few minutes to discuss what's out there. Why is computer science important? Not just for programming, not just for turtles, for data crunching. I'll give you a couple more minutes. Plenty of time today. I think I've given you an essay about one thing that you could write about, right? About art and computer science. All right, that's my timer. What are our ideas? Did we think of any? Cool. Let's think about them. So yeah, just people drawing with computers or making digitally rendered things. I think that's a great example of how art has been influenced by computer science. Very nice. So yeah, everybody's making video games, animated movies are no longer hand-drawn, right? Everything it's got a computer in it somewhere. Good. What else? What else? Oh yeah, technical theater. Very nice. Yeah, so if you're going to, like, something that you wouldn't expect, like a play, if you're going to watch one of those, a lot of the lighting, the sound effects, those are all, you got like a switchboard in front of you these days, don't you? That's pretty cool. There's a lot of software behind that I wouldn't have thought about. That's a great thing to bring forward here. What else? Virtual production. That's true, yeah. If you're going to do 3D modeling or something, which I would consider just to be computer science in itself, but that would involve some coding. Or somebody has coded the engine that you're going to make your 3D model in. Yeah. AI art is probably the hot new topic, right? You have, what is it called, Dolly and all those other Midjourney, all those other software things that use artificial intelligence to generate images, which is contentious these days. And yeah, just anybody making computer-generated images, whatever you want, just even Photoshop. Great thoughts. Any other questions, comments about any of these? So yeah, these are great examples to realize that computer science doesn't exist in a vacuum, right? People in all over the fields that are not computer science are taking advantage of software written maybe by a computer scientist or by someone else. So that's the idea. And so I just have a few examples to share with you for this topic, and just to get your brain moving after break. And then I have one more topic that we'll go through. It's a bit more sciencey, I guess. So did I forget to delete that? Sorry. Let's talk about computational linguistics. That's a very important place to think about. ChatGPT, I guess, would be considered to be a computational linguistics place. It's more just hardcore machine learning, though. So computational linguistics, I can't remember if I've told you about this or not. It's when you have a computer or an artificial intelligence engine, and you're having it process usually text or maybe a voice recording. So it's when you have a computer do stuff with human languages. It's not like you're coding in Python, that's a computer language, but you're feeding English, you're feeding Spanish to a computer in some form, either auditorially or with text, and it's processing that information to extract stuff, to respond to you, stuff like that. And so something that a problem that is mostly solved these days is speech recognition, I would say. So you're talking to Siri or to Alexa, and they can pretty much understand exactly what you want, right? That did not used to be the norm even a couple decades ago. So that's more of a recent advance, I would say, speech recognition in general. And that's converting audio waveforms to text that can then be processed, right? That's cool. You can also throw that in reverse. You can ask computers to respond to you through a speaker and have them speak to you. Speech synthesis is just a topic that has been around for a very long time. Even like the very first Macintosh computer had speech synthesis, and it was so cool, and you could mostly understand it. Nowadays, of course, Siri, Alexa, it's speaking words that it has never been trained to speak. It just knows the sounds that well. And so computers are very good at talking to us these days. It's another mostly solved problem, I would say, speech recognition and speech synthesis, but very cool problems to have solved, I would say. And then probably the coolest piece of computational linguistics is just the generic term of natural language processing, or NLP for short. They took the first 3 characters of this word. And here is a quick little paragraph, or a quick little sentence to talk about what natural language processing is meant to do. It's meant to, think like a human. It's the ultimate objective of NLP is to read, decipher, understand, and make sense of human languages in a manner that is valuable. So it's very generic. NLP I think I told you it's used for hate speech detection on certain social media websites. It's, of course, I guess you could think of it as the backbone of ChatGPT as well. It's a hot problem that people want to attack. All right, so that's NLP. And yeah, that's led to, in addition to ChatGPT, like all those websites that pop up and say, hey, I know it's 3 a.m., but this is really a human right here ready to respond to you. And you can ask your little question, click the button, and it usually gets it right, whatever you're looking for. So that's not a real person behind the screen at 3 a.m., but a piece of software doing natural language processing, which is really cool to think about. Computers are here to help us these days. So yeah, that's computational linguistics in a nutshell. Any questions about any of that before I get into like a bigger example of it? Yeah, hopefully we've heard about just vaguely some of these concepts so that I can make them more concrete. But yeah, let's talk about what NLP does. Like you're talking to Siri, you're talking to Alexa, or Google, whatever it is, and you say something. What is happening? What is happening behind the scenes? What is natural language processing doing to get at our end goal of whatever we're asking it to do, right? So the first step, right, is you say, hey Siri, or hey Alexa, or whatever, and then you give your command, set a timer for 5 minutes. So you say that with your voice, right? So the very first step of natural language processing is usually speech recognition in this case. It needs to convert, which is a hard problem, but we've mostly solved it these days with the help of some smart people and their ideas. We have to convert voice to text. That's the very first step. And that's not immediately apparent, right? So when you talk to Siri, it's figuring out what you said by converting your speech to text. And so I'll just rewrite it again. Hey Siri. So it went from voice, which is in black, to text, which I guess is in blue. Set a timer for 5 minutes. And then when it has text, it needs to process that text as if it were a human, how a human would process it. And so it needs to like do that diagramming of sentences that you did in elementary school. So it needs to notice like the hey Siri, it needs to discover those words and understand that that's a sort of an activation for it, right? That turns on Siri and it makes Siri listen to the rest of the sentence. So that's like an activation. That's probably the easiest thing to check for. It's just like, hey, are the first two words exactly equal to hey in Siri, or in whatever language you're using Siri in? That's the first thing to check for. That's just like, are these exactly equal? And then it needs to parse the rest of the sentence as if it were a human, right? It needs to figure out what you want. I want a timer set for 5 minutes. How does a computer discover that? So it's going to break down the sentence just like we did. Hopefully we still do in elementary school, right? We understand that like set, that's a verb, that's an action. Something, I want something done. So set is the verb, and it's a transitive verb, right? So it takes an object. What do you want set? I would like a timer set, please. So it needs to discover like this object is associated with this verb, all that fun stuff. And then there's a prepositional phrase or whatever for 5 minutes. That's going to give you a duration. That's modifying the timer that you want set, because it makes no sense to just say, hey Siri, set a timer, because you have to say for how long. So there's a duration. And so this is what the backbone of Siri's natural language processing engine is doing once it converts your speech to text. It's figuring out, hey, what do you want? Okay, set a timer. I understand. For how long? Okay, I get it. I can do that thing that you want to know. Okay, so it's a bit of an involved process, but we can do it these days for simple things like this, at least, which is, I think, is pretty cool. I hope that we are as excited about the future as I am, because it can only get better from here, right? Maybe ChatGPT one day is going to be hooked into a voice prompt and can respond to you just like Alexa or Siri can. So yeah, that's NLP. Let's see. For my next topic in social science and art, this is more of a social science, I would say, linguistics. Let's talk about human-computer interaction. And oops, I had some white lines and I was looking at this with a glare. So I'll be redrawing these, I promise. Come on. There you go. So let's talk about human-computer interaction, because it makes our lives so much better. What human-computer interaction is, by the way, if you've never heard this term, it's a bit of a computer science-y term. It's the study of the interfaces between humans and computers. So like I am using Windows, I'm using PowerPoint, has all these buttons that I can click. That idea of having a button to click, of having a mouse to click with, that was all created by human-computer interaction researchers, okay? So it studies the interfaces between humans and computers, and of course, some of those interfaces work for not just humans, like cats can play video games now, which is pretty cool. But yeah, these researchers, human-computer interaction people, we need to say our thanks to them because they're the ones who gave us graphical user interfaces, they're the ones that gave us mice. Technically, Xerox started all that, which is very nice of them, the copier company, for some reason. And Apple stole all their ideas, but they were just given to them for free. So back in the day, right, I don't know if you've seen this, maybe if you've taken Computer Science 40, you know what I'm talking about, but before there was graphical interfaces, there was a computer screen with a terminal on it, and it looked like this. You could say, I don't know, you could give it commands and it would show you textual results, and that's how you interacted with a computer for decades. That was how it all used to be. You had just a text place where you could type your little commands and they would execute. No graphics, just a big wall of text. And that's how people interacted with computers from the beginning. That's like before human-computer interaction people got into the mix. So it was a bit more complicated to use a computer, I would say. And then, next in the series, right, came Windows, graphical user interfaces. That was something that people had to like discover and think about the best way to do it. So let's make a bunch of different window panes where you have different programs running. That's a fancy concept, right? That's something that did not exist for a while. And so people had to come up with that. All right, the X button. Everybody's going to know across languages what that means, and it's always going to be in the upper right. We're going to do that. We're going to make that standard. Okay, so first was text, then came Windows, and like the concept of a mouse, and dragging things and pointing and clicking, because that, again, when it was all text, you just interacted with a computer with a keyboard. There was no concept of a mouse yet, but now with Windows, you need a place to point. You need a place to drag with your stylus as well. And I guess the ultimate end goal for some people, maybe it's died a little bit. Like Facebook tried really hard to make it a thing, and it's never going to be a thing probably, but virtual reality or augmented reality is perhaps the final frontier of humans interacting with computers, right? Just overlaying maybe the software on top of what you see if you have some goggles on or something. And so, the more recent advances is in the augmented reality stage, where I think the most common example that I could give you is Pokemon Go, even though it's maybe not the most popular thing in the world anymore. But what that is it's a great example of having an interface drawn on top of the world. And that is probably the easiest thing for a human to understand, right? If I want to interact with a program and it's just being drawn on top of the world for me, like I can interact with it like I would interact with a physical object. And so that's going to make it very easy to do things, I would say. And so this is Pokemon Go, of course, and it's like you have your little camera and it's overlaying the Pokemon that you want to catch on top of that. And so what it needs to do, what all augmented reality software needs to do is they need to like use their gyroscopes and use their cameras and find the horizon. They need to understand like, okay, the world is flat right here, so I can draw a Pikachu not on a hill. All that kind of stuff, that's processing that needs to take place somehow. And it will make it look a bit more interactive and a bit more real that way. And so there is some computational stuff that needs to go on, but I think that is perhaps the ultimate goal of interacting with the computer, making it look like it's a real object in front of you. Any questions, comments about that? Do we agree? I don't know. Is this what we want? I don't know. We'll find out one day, I guess. So, I think another great example of just not like Photoshop-y art is music. So, music production is more or less digital these days. I think you have to be a very, very obscure indie artist to just record anything on it, like with tapes these days, but some people still do it. But just music in general we can thank computers for all of it that we have today. So like if you like electronic music, for example, you have computer science, right, to thank, because the first synthesizer was a digital device. It was made with circuitry. It was made with computer science and computer engineering concepts in mind. So Yamaha, apparently, in 1974, made the first digital synthesizer. And then, of course, that's made its way to a lot of music these days. There's plenty of software that people like to use to record music, and it lets you just like have a virtual mixing interface in front of you, like Logic Pro from Apple or Ableton Live, all of these things that maybe you've heard before, but they are super, super common. Just like award-winning artists are writing or producing albums with software these days. It's not just a big room of tapes being recorded anymore. Okay, so that's important. It like kind of opens up the field for more indie artists, I would say. It's easier to make a professional sounding album with this kind of software. It's not as expensive, of course, as a giant recording studio. And then also, just like if you want to do stuff with the instruments that you own, you can with software. It can emulate fancy things. Something near and dear to my heart as a guitarist is like you can plug your guitar into your laptop, and like GarageBand or all of like Logic Pro, it can emulate these very, very fancy and expensive amplifiers that you cannot dream of ever affording. And that is a beautiful, beautiful thing, I would say. So like here's your little guitar that is electric, I guess. You plug that in to your computer, and it can make it sound like you're in a giant room. It can make it sound like you're running through a very expensive amp, and it just they've figured out how to make it sound like that and make it convincing, which is really nice. You can pretend to be a big star that way and make some very nice sounding music. So I think music production and computer science go hand in hand these days, which is important to say and important to think about. Okay. And then finally, I think for this last topic, let's go into art itself. Of course, we have Photoshop, right? Another two-dimensional pieces of software, but you can also think about 3D software, can't you? So I saw this quote somewhere on the internet, maybe on Reddit, but somebody said that the best composers of our time are probably the ones writing music for movies. Like, think of all your fancy theme songs that you know these days, written by composers. That's probably where all the money is. And so maybe we'll look back one day and say, like, oh, this dude who wrote the Indiana Jones theme was the greatest composer ever. Something like that. Because maybe that's where the money is. And something could be said then about maybe the best artists of our time are the ones painting digitally, because that's how they're making their money. Like making assets for video games or making digital art to get and send to millions of people rather than just making one piece of canvas and like filling that with something. So they're probably, if not the most talented people, many talented artists are working completely digitally these days, and that's why I gave you that essay to think about, right? And that's maybe because of the money. Maybe they're following the money. That's how you reach the most people. You have a Twitter account. You're sharing your art. You can make as many prints as you want of it if it's digital, right? So that's 2D art. That's going to be around forever, of course. But there's also 3D art. There are open source pieces of software, for example, Blender, where you can make and edit 3D models and maybe sell them to people to be used in video games or to make your own video game or make your own animated movies. And there's ways of sculpting, essentially, to make these 3D models. You like press into your digital pen device, and it's like you're carving away at virtual clay. It's really cool. But yeah, it's essentially where the sculptors are going, maybe, these days. 3D artwork, and making that is potentially the most lucrative place for you. And so art is moving digital, and I don't know if that's a good thing or a bad thing. You tell me in your essay, of course, but that's something to consider. So yeah, I think that's what I wanted. Those are some examples that I wanted to give for social science and art. Are there any questions, comments about any of that? because I want to go to a more technical area, and that'll be it for the day. So just get our brains working slowly but surely with one more topic. Let's talk about medicine and science, maybe more near and dear to our hearts as people who chose to take a computer science class. So let's talk about how computer science has affected medicine and like hard sciences like physics and chemistry and things like that. So again, I would like you to think about this for a few minutes. So again, with your group, go back. I'll clear this out one last time. Please write down some examples that you can think of computer science software being written or just being used in the medical field, in the fields of like harder sciences like physics, chemistry, biology, stuff like that. See what we can remember or think about. And then I have, of course, some examples to share as well. So take another few minutes to think about that, and then we'll come back and discuss. Take about another minute to write down all your examples that you can think of, and then we shall discuss. Alright, that is my timer. I hope that was enough time to think of some stuff. Write it all down. What we got? Alright, yeah. Maybe medical machines, we're thinking, group 46. If you want to get information, assuming you're talking about, I guess it could apply to science as well, but if you want to get patient data is all stored on the cloud these days, of course, you have, and then if you're just doing normal, data gathering, if maybe you're a chemist or something, you're tracking some experiment, you're going to put all that data in maybe R or some other statistical language. So yeah, that's a great place to think about. Let's see what we got. Definitely, yeah, on the more engineering side in medicine, you have machines that are meant to do something that only a doctor could have done back in the day, right? So we have fancy machines to do stuff, and of course they're programmed by some computer scientists somewhere, I'm sure. And yeah, X-rays are now mostly electronic these days, which is interesting to think about. You go to the dentist, it's not like an actual slide of your X-rays anymore, isn't it? That's crazy. Yeah, definitely. If you think about hospitals and the data that they collect, it's not paper anymore. That's a great thing to notice. Yeah, so good thoughts here, everybody. Let me just read through the last couple. Oh yeah, just surgical machinery to make the outcomes more, I guess, better outcomes for people if a machine is operating on them sometimes. Yeah, exactly. There's even, I think I read about a surgeon virtually across the country operating a machine that did surgery on somebody. Or maybe that's the great thing that you're talking about. That's pretty cool. Maybe that's the future. Yeah, and just at the end of the day, this is exactly right. Computers are meant for calculating things faster than a human could calculate. And so if you want to do any kind of simulation, if you want to do anything at all, any kind of real data crunching computation, and you want it done today, a computer is usually the right thing to look to. So these are great thoughts. Yeah, and just the amount of knowledge you have in front of you with a computer, with the internet in front of you, all of that at your fingertips as a doctor is super, super helpful, or just as anybody working in any job, I would say. So yeah, great thoughts. Any comments after I read them? Any thoughts to share? Before I tell you my ideas, I don't think. I think I tried to find some out there ideas that are not the ones that you would think of, and I think I have succeeded. I don't think anybody said any of the things that I talked about for the rest of these slides, so that's exciting to me. So let's talk about some maybe places that you might not immediately remember or see computer science being used in the medical field, in the scientific field. One that is maybe very near and dear to our hearts on this very, the first hot day of the year, is weather forecasting. And so this is where computers can really shine. It's a simulation. So more or less these days, you can essentially, what weather forecasting boils down to is you have to run a simulation. You're modeling what's going to happen in the atmosphere, and the atmosphere is full of air and gases and things and clouds, and so that's it's a fluid. You have to use the fancy physical fluid dynamics equations, and there's a lot of heat moving around, thermodynamics equations. You have to plug all that in and have it figure out what is going to happen. Run that simulation. That's what weather forecasting is these days. Okay, so here's essentially what happens. You take a chunk of the Earth that you care about, that you want to forecast in, maybe this is the Fresno area or something, and you take maybe some readings. There's a bunch of sensors placed all around Fresno, and it's keeping track of, right, what's the temperature at this place? What's the temperature here? What's the wind speed over here? What's the wind speed over here? What's the atmospheric pressure? And so you get a bunch of little readings from all over the city or something. And so you have a big 3D cube of how the air looks based on these sensors. And that's we've recorded that at time A, at 4:38 on a Monday. And the goal of weather forecasting software, these simulations, is to predict what's going to happen, what this same little box of air is going to look like at time B. That's really all it is. Like, all right, at those same places, or just like you can extrapolate to any place inside of it, inside of this box, like, okay, the wind's going to be moving this way. It's going to be this hot right here. The pressure is going to be this, etc., etc. So that's all weather forecasting is. It's like you are going to model what the air is looking like and all the features of the air that you care about, like temperature and pressure and things, wind speed, humidity, all that fun stuff. You can do that. So with enough sensors and computers that are fast enough, like you have to run this through a supercomputer, or more or less a large amount of them, you can more or less make some accurate predictions. Weather forecasting has gotten better than it used to be, of course. With faster computers and more sensors, you can model more things and you can get an accurate prediction. Like now, the weather a week away is pretty accurate, whereas a couple decades ago, it was kind of a shot in the dark, which is really cool. All right. So yeah, that's weather forecasting in a nutshell. And so it's never the weather person's fault. It's the fact that they need a stronger computer and more sensors all over the city, essentially. So that's weather forecasting in a nutshell, and that's really cool. I think it's getting better as computers are getting better. Other things that we probably care about as Fresnans are air quality. Making an air quality forecast is essentially the same as doing a weather forecast, right? Because you need to plug in, all right, where's all the pollen coming from? Like where are we in the season that we're in? What's the wind speed that's going to move around? The fires, all that fun stuff, all right? So that's very similar. Air quality forecasting is very similar to weather forecasting, though sometimes the weather's forecasted wrong. Sometimes the air quality is forecasted wrong. It's simulating based on what it knows, right? It's simulating based on, all right, a bunch of days of this kind of lead to this other thing. If you have some weird weather, some unprecedented weather, the models are going to get thrown off very easily. And so if you remember the giant wildfires that we had, multiple of them at the same time a couple years ago, that kind of threw off the air quality forecasts, the weather forecast, because like the sky was blacked out. It was actually cooler those days, wasn't it? So that's a little interesting, right? These models were just like given a curveball, and they couldn't really deal with it, because what they were doing, again, they were making predictions. They were doing these simulations based on what they were trained with. They had some training data. It's essentially machine learning. So, like, based on what they've seen before, they had no clue what was going on with these giant wildfires, okay? So that's crazy. That's fun to think about. And that, I guess, leads into the last idea of, I guess, weather forecasting is you can simulate what a fire is going to do in the same way that you can simulate what the air quality is going to do, what the weather is going to do, because you have the same information, right? You have, like, this is what the fire looks like now. This is the way the wind is moving. This is like the readings. We can simulate, like, okay, we think the fire is going to like advance over here and over here, but not so much down here. And so that can help the firefighters, of course, advance and put out the fire before it gets to be too horrible, and like hopefully fight it a little bit better. So you can simulate that as well. And so all of these things are helpful to humans, I would say, and powered by computers and modeling that is done with them. Any questions, comments about that? That's a fun thing, I think. Maybe you'll be a weather forecasting software engineer one day. So yeah, lots of things that are not normal. I'm going to make a website or an app that we should definitely talk about. All right, what else? More towards the medical field, you have genome sequencing that is cheaper and just possible nowadays, which is really cool. And so one of the fanciest things, back in 2007, everybody was very excited about it, apparently. I was not following the news too much, but I'm sure maybe our parents were. But that was the first time, back then was the first time that we were able to pretty much completely, modulo a few things that were not very important, sequence an entire piece of human DNA, the entire genome. And so what that is, right, is you have your DNA, you can extract it from one of your cells, it's always the same, right? And you what sequencing means is you convert that to the base pairs that are in DNA. So like this is like A, T, G, A, C, whatever order it's going to be in. That's what DNA looks like. It's extracting that. So that's what genome sequencing is doing. And this was a huge effort. There's like billions of these base pairs or whatever they're called. And so that took definitely computer science, and it definitely took some engineering machinery that needed to be created. And that allows us to like look at our own DNA all at once. And that was something we definitely couldn't do before. That's very exciting. And that's led to more consumer grade products as well. If you've used 23andMe, I have not. Sounds fun though. If you've tried that, that is based on the successes of genome sequencing. It's not as fancy, I would say. It's not sequencing your entire genome, but it's doing important pieces. So that also, surprisingly, started in 2007. That's when all of this interesting stuff happened. So if you've never used 23andMe before, let me try and explain it to you. What it does is like you take like a swab of your saliva or something, and you send it into these people, and they are going to tell you, I guess the original thing that they did was they told you your ancestry based on your DNA, and they still do that, of course. And so it's like, all right, here is my best drawing of Europe. It's like you do the little swabby thing, and it's going to tell you, like, all right, you have some ancestry, and here's Africa, and you have some ancestry from here, all these places, down here too, all this stuff. Okay, and it's like giving you percentages of your ancestry based on your DNA, and so that's really cool. That's what they did, and after that, nowadays they also look for markers in your DNA that are indicative of genetic disorders, which is another important thing to look for. And so what the 23andMe people are doing, they're not sequencing your entire genome. They're essentially looking for pieces that they know about. So like here's a drawing of a strand of DNA, I guess. And so they're not actually sequencing your entire genome because that would be too expensive right now. What they're doing is they're looking for little markers. They're like, all right, this marker means you have North African descent. This marker means you have Western European descent. And so they're looking for those markers inside of your big DNA. And so that's apparently cheaper and easier to do than sequence an entire genome. So that's what it's looking for. Like this marker indicates that you will likely end up experiencing some sort of genetic illness. And so that's definitely something you want to look for. And so that's essentially what 23andMe is doing, which is fun to think about, I think. Have any of us tried it? I still have yet to try it, but it's supposed to be not too expensive these days, I think. Tell you your ancestry, make sure you're healthy. So that's fun to think about. And so that's medicine. On the same in the same vein, you have medicine plus engineering, of course, and we've seen some recent breakthroughs in robotic appendages like arms and legs, which is cool. And so here's a picture I will try to explain. But we have made a robotic arm recently that is non-invasive, which is fun and exciting. So let me try and explain to you the difference between all these terms. I am, of course, a computer scientist and not a doctor, or not the medical doctor kind. But let's learn some terms. So if you do, let's see. I guess first of all, let's pretend we're talking about a robotic arm. Okay, that's where I'm going with this. Let's talk about how they work, because it's definitely a combination of software and hardware. So let's go there. If you have a working arm, for example, what happens when you want to move it, right? You have to send signals. Like you have to think that I would like to move my arm some way or somehow, and then that information gets translated and moved into another part of your brain, which is actually responsible for doing the movement. So the motor cortex, I guess, is where the movement happens. So you have to think that you want to move your arm, and then you have to like send that signal to the motor cortex of your brain to do the movement, and then it sends some electrical signal down to the muscles in your arm to actually finally perform that movement. Of course, all of that happens in a blink of an eye, but that's what happens if you have a working arm. And if you have lost your arm, there are some options for you depending on what is going on and depending on the nature of the problem. So if, for example, you had your arm amputated, then you would be fitted with a prosthetic arm. So I'm trying to teach you the difference between prosthetic arm and robotic arm. So in a prosthetic arm, your brain is still fine. It is sending signals, like you can still think that you want to move your arm even though you don't have one anymore. You can still send signals to your motor cortex, which can send electric signals down to the end of your arm, wherever it stopped before it got cut off. Then that can be used, you can hook into the signals down at the arm with a prosthetic arm. That's what I'm trying to say. And that can be used to move the prosthesis, which is very exciting and awesome. That was definitely not possible before you were able to hook into this electrical signal. Fast forward to a robotic arm. A robotic arm is different from a prosthetic arm, and I did not know this before I researched this, so that's why I'm spending time on it. But a robotic arm is when you have a damaged spinal cord. The motor cortex cannot send the information to the edge of wherever the rest of your arm is, like to your shoulder or something, or to your elbow, wherever it was removed. That is where the robotic arm comes in. It is hooking up not to your shoulder or wherever like the closest area is, it's hooking up to your brain. So you're putting little pieces into your brain that are going to like go to the arm area of your brain and have that move the robotic arm. So that's the difference. You're hooking into the brain itself to get the signal because the signal is not being transferred properly anymore. So back in the day, before this new breakthrough, you had to essentially like drill into somebody's head to get and place little electrodes where they needed to be to move this arm. But nowadays, there is a new breakthrough where you can make a robotic arm with somebody with a damaged spinal cord. You can put little sensors not inside of their brain anymore, but just like on top of their head or something. And that will send signals, it will get the proper signals to move the robotic arm, which is really, really exciting and awesome. No longer invasive. So that was 2019, so just a few years ago. That was the first non-invasive robotic arm. And I would say that's definitely a huge quality of life improvement for an amputee or for somebody with a damaged spinal cord. That's awesome. So yeah, you don't have to like drill into somebody's head, don't have to perform some invasive surgery to get into the brain, just put some sensors on somebody's head and they can like have an arm. It's really awesome. So that is robotic appendages, a hot field that a lot of advancement is happening in. Any questions, thoughts about that? So that is the difference between a prosthetic arm and a robotic arm. I did not know, and so that's why I'm teaching it to you. Okay, so I think I have 3 slides left, and let's talk about the rest of these examples. I think, again, as Fresnans, we're probably very interested in this idea because that's feeding our economy. Smart farms, introducing technology into fields is something that people care about these days. It can make your farm better. So farmers nowadays, they're able to put sensors around their fields to like monitor the soil. Like you're sitting in your house, it has some sort of receiver like on the top of it, and that's pointed at the little field where you're growing your crops, and it can tell like, all right, here's what the soil is like, here's what the how wet it is, things like that, and so you can better plan for how to grow your crops and how to efficiently make them succeed and get lots of money. So yeah, that's one thing. Put sensors everywhere, and that those sensors can be maybe powered by the sun. It's really, really cool, and they can it's essentially a mesh network. Like they're all talking to this receiver here, all the sensors, and in the comfort of your own home. As a farmer, you can look at all of these properties and make decisions based on them. That's fun. Another cool thing to think about is you have self-driving tractors I think they're much more common than self-driving cars because nobody can get hurt with a self-driving tractor. You can use GPS. And so first of all, it's your land, and like what you can do with a self-driving tractor is you can like set up GPS coordinates for here are the 4 corners of my plot, self-driving tractor. do not go outside of them, because then you'll run somebody over. And you can just tell it, like, all right, plow, go this way, then turn around, go this way, then go this way, then go this way. And like once you're done, go back into the shed. That's much easier, right? That's like a Roomba at that point. It doesn't have to worry about traffic. It is self-driving for all intents and purposes. There's no traffic rules either. And yeah, so you can just, like, if the GPS satellites are working, and they're usually working, then you can program a tractor to drive itself and plow your field, harvest things. That's super cool, I think, and that's where the technology is headed, I think, as well. So yeah, I've also heard of, there are some fancy companies using artificial intelligence. They have sensors on these self-driving tractors that are looking at the soil, and they can like send a high-powered laser beam into only the weeds, which is fun to think about. And so there's some cool technology coming out of these ideas. And then also, just like when you have all these sensors, you can gather a lot of information, and then it becomes big data, and you can use that to feed that to machine learning models and have it make predictions about what you need to do. Like, you better water now because your soil is not super dry, but it's eventually going to become dry. I'm going to predict that. Things like that. So yeah, with more sensors, with this giant network, you can make better predictions for how to grow things, which is fun. I'm not a farmer. I do not know any farmers, but maybe you do, and you've seen some of this. It's fun to think about. All right, let's see. How are we doing on time? Oh, plenty of time. So yeah, I just have 2 more slides, 2 more examples, just to get our minds working, just to understand that, like, it's not just people writing software for phones or people working at Microsoft and making PowerPoint or something, people making websites. There's a lot of computer science outside of the standard computer science areas. One, of course, that is very necessary is space. If we want to do something in space, usually we're going to send a ship, we're going to send probes, we're going to send rovers. We can't have a human on Mars right now. It's too hard to get humans there, but we can totally have rovers there, and they're all powered by machines, right? They're all mechanical, they're all being coordinated with software sent from Earth. So all of space technology is made possible because of computers. So the first example is, like, we have all our fancy telescopes, both in space and on Earth, and we can have those coordinate with software. Like, here is some country, and let's say we have a telescope on Earth and we want it to, like, focus on this star. We can have it track it because the Earth's moving, the star is moving. You can just, like, keep it centered. You can do the same with a space telescope. Here's my best drawing of a space telescope. But you can have it control itself and, like, point here, look at this thing, and just keep tracking it as you're moving. That's really cool. That's all software-based. Satellites, of course, software-based. GPS, we have all of that. Satellite TV used to be a huge thing. Satellite internet is now a huge thing. And then, yeah, just any rover, anything that we send to somewhere else, the space shuttles, they're all powered by software. The Mars rover, for example, it's getting, I don't know if it died yet or not, I haven't looked into it recently, but the Mars rover, it at least got commands from Earth, from Houston or whatever. And it's all software being translated to movements in the rover, telling it to take pictures, turn this way, take another picture, stuff like that. So that's a great example of software being used to, like, further human knowledge, which is fun. And then probably the coolest example, I would say, I don't know if we've heard about it very much because it's very technical, but I think in my mind it's one of the coolest things that computer science has to offer. It's another kind of simulation. It's called protein folding. Anyone has heard of that? It used to be, in 2020, there was a big breakthrough, but it's always been around, and it's a very, very important thing for medicine. So the same people who made the Go game artificial intelligence made a protein folding machine learning software. And what protein folding is it's a way to predict protein structure. Again, I'm not a scientist, I'm not a biologist, but if you have a protein, it's made up of a bunch of amino acids, right? And apparently, just the way that it's built, the order of the amino acids cause it to like curl up and coil and do weird things in three-dimensional space. That's what a protein looks like. It's not just like a big strand of amino acids, just the fact of like its surroundings and the exact order of those amino acids cause it to curl up and twist around, and it has some shape, some three-dimensional shape, and that allows it to interact with other proteins in weird ways and be like a catalyst and do all those fun things that proteins do to make our lives better as humans and like help out with medicine. So that's why proteins are important. And if you come up with, like if you're a pharmaceutical company, you come up with a new drug, essentially it's usually a big chain of amino acids. And so you want to know how that drug that you just made, how it's going to fold, because that will tell you how it's going to affect human cells, human proteins, other things that you want to care about. Okay, so that's what it is. And there was a machine learning piece of software called AlphaFold 2, and there was like a challenge that it participated in, and it totally blew everybody out of the water in that challenge. And it got like 80-something% correct in terms of how it predicted that proteins would fold. They even thought they cheated. And so they had to give it a brand new protein that nobody had ever looked at other than a human. And it predicted that one's folding correctly as well, which is really cool. And so yeah, that is protein folding. It's very, very helpful because we want to make medicines. We want to predict how proteins look so that we understand how they interact with other proteins. That's what it means. I guess that's the whole point of a protein. It needs to interact with other ones. And that will help us understand how our cells are moving things around, and that will help us make medicine that can attack certain issues inside of a cell. Have it like curl up next to this problem and deal with it. So that's my best computer science explanation of protein folding, but it's a great example of machine learning and a great example of, I think, just computer science in general. Yeah. Any questions about that? Maybe I've jogged your memory. Have you heard about it? So yeah, it's just fun stuff that it's not turtle programs. It's not just like games or apps. It is things that non-traditional computer scientists use. Medicine, science, social science, and art. So yeah, I think that's everything that I wanted to talk to you about today. So thank you for your responses here. And I know that we had an extra credit due before, and so I'm going to give you another one that'll be due on the last day of class, but I'll talk about that next time. Okay, so that is all that I have for us today. The rest of the time is yours to work on stuff that is out.